Okay, I've decided we're going to go ahead and start chapter 6 here. So, our last two chapters, chapter 6 and 7, are all trig. And since I believe trig may have been a prerequisite for 129, I think you should be pretty good at trig. So I'm just going to go over some quick basics. I'm not going to spend a lot of time on it. So you know trig, which is all about circular functions or functions of an angle. And we're going to talk about periods and how it's periodic as we go into our graphing, which is for a few sections. So just some things that you need to know, some vocab. So when you have an angle, you know that this is the vertex of the angle. If an angle is in what we call standard position, it means that you have the initial side on the x-axis. So you can see that there it looks like it's horizontal, or it would be on the x-axis. The terminal side can be in any one of the four quadrants. It's where the angle ends. And of course, this measurement right here, and we measure that in two different ways, in degrees and in radians. That measurement right there is the measurement of an angle. And if I'm going from the initial side up to the terminal side, that's a positive angle. In other words, I'm going counterclockwise. If you go from the initial side and you go down clockwise to the terminal side, then you're talking about a negative angle. And then, of course, if you start at your initial side again and you again go counterclockwise, you can go more than all the way around. And you could, of course, end again and that terminal side. So all three of those measurements would give you the exact same angle. You could measure from here up. You could measure a negative angle from here all the way that way. Or you could measure all the way around 360 degrees plus a little bit more. Okay, so we're going to use a lot of Greek letters when we're talking about trigonometry. So probably the most common one is theta, but there's also a couple of others. If you see this symbol, that is your alpha. This one looks like a B, it's beta. And this one that kind of looks like, I don't know what it looks like, a V kind of, but that is gamma. And we'll be using, again, lots of Greek letters. But theta is the one that you use most often for an angle. So an angle, theta, is said to be in, and we just talked about this, standard position. If the vertex is at the origin, the initial side is on the x-axis. And again, we can measure an angle going counterclockwise, that's positive, or here we can measure it clockwise, that would be a negative angle. So when we say that it is in standard position, the terminal side will lie in any one of the four quadrants. Okay, and then we say that that theta lies in a quadrant. So for example, here my theta would lie in quadrant 2 because that's where my terminal side is. Here my theta would lie in quadrant 3 because that is where my terminal side is. Okay, now, or it can lie on the x-axis or the y-axis, in which case we say that the angle is called a quadrantal angle. And again, what that would mean is if you had the terminal side here, and let's say you had the very famous 90 degrees, because that terminal side does not lie in a quadrant, it lies actually on the y-axis, that would be called a quadrantal angle. Okay, so we're going to just kind of read through this explanation. This exploration. We're not going to spend a whole lot of time on it. So thus far in our math career, we've always measured angles in degrees. 360 degrees, of course, makes a full rotation and represents one complete counterclockwise revolution around the circle, which means that 1 degree is 1/360th of a complete revolution. And of course, 60 degrees represents 60 over a total of 360, or 1/6 of the complete revolution. From this, it should follow then that a right angle is 1/4 of a revolution counterclockwise and is 1/4 of 60, which is 90 degrees. If you look up at the top of the second page, a straight angle is actually 1/2 of a revolution counterclockwise, and then it's 1/2 of 360, which is 180 degrees. So when you're drawing an angle, you're just kind of estimating it unless you actually use a protractor, which we are not going to use any protractors. But you always want to draw it in standard position. So there's the vertex of the angle. Our initial side is on the x-axis. Now, if we want to draw approximately where 135 degrees is, if we want to move, now remember this is 90. So we want to go another 45 degrees, which is going to be about halfway into the second quadrant. So this angle right here, we'll call it angle beta, is approximately 135 degrees. If we want to draw a picture of a negative 120 degree angle, again, we'll put it in standard position. So there's the terminal or the initial side. And if I go down clockwise, that's going to be 90 degrees. And then I need another 30 degrees to get to 120. So it's about right there. So this angle right here, we'll call it alpha, is about negative 120 degrees. So we don't use it very often, but we can talk about degrees in degrees, minutes, and seconds. So when you have a degree, every degree can be divided into 60 parts, and those are called minutes. So you can picture they're very small, and then every minute can be divided into 60 parts, and each one of those is called seconds. So in a full circle, there are 360 degrees, and again, each degree is split into 60 parts, minutes. So 1 minute would be denoted by 1, and then we would use this symbol as minute, and it's 1/60th of a degree. So 60 minutes equals 1 degree. And then 1 second, which is denoted by 1 and then 2 little marks like that, is 1/60th of a minute. So there are 60 seconds in 1 minute. Which means, by the way, that there are 3,600 seconds in 1 degree. That follows logically. So now, if we wanted to convert 45 minutes, or 45 degrees, 10 minutes, and 15 seconds into decimal form and round the answer, here's what you would do. It's 45 minutes, so that's easy, plus, and then it's going to be 10 times 1/60 because it's 10 minutes, and then plus 15 times 1/, and it would be 60 times 60, or 3,600. So you would just do that math in your calculator, and it says round to the nearest fourth. So I actually haven't done the math in my calculator, so I'm going to go ahead and do that. So 45 plus parentheses 10 divided by 60. Oops. Plus parentheses 15 divided by 3,600. And I got that is 45.1708 degrees. Okay. If we wanted to convert this decimal into degrees, minutes, and seconds, here's what we would do. Well, we know that there are 12 degrees, so we already have that. We have 0.87 of a degree. So what you're going to do is you're going to take 0.87 and you're going to multiply it by 60. Well, if I multiply 0.87 times 60, you get 52.2. So right now we would have 12 degrees and 52 0.2 minutes, but now we have to take care of this decimal. So what we're going to do there is we take 0.2 and multiply that by 60, because we know that there are 60 seconds in a minute. And when I do that, I'm going to get 12. So what that tells me is that there are 12 degrees, 52 minutes, and then that part of a minute is, whoops, I marked that wrong, sorry. And that part of a minute would be 12 degrees. Okay, let me say that again. So it's 12 degrees, 52 minutes, and 12 seconds. All right, let's keep going. So the other way we measure angles is called radians, okay? And radians have to do with the arc length. And the arc length is this right here. So for example, the arc length of this, and it's a little s, would simply be if you were to literally take scissors and cut this circle there and lay that measurement out and measure it. If I measured it straight, I would get the arc length. So the arc length is a linear measurement, okay? And here's a formula for you. Your theta is the arc length divided by the radius, which in this case is s divided by r. Since the radius and the arc length are measured in the same units, theta, or the radians, do not have units of length. So if we solve the equation for s, we get the following formula. So if I just take this theta equals s over r and solve it for s, what we're going to get is we're going to get a formula for arc length. So if I solve this for s, if I just cross multiply, you can see I would get s equals r theta. And that is our formula for arc length. So that will tell you how long this arc is. Something that you have to make sure that you understand is that your theta always has to be in radian measure. That's what this says right here. So if I go ahead, it says find the length of the arc of a circle of radius 4 subtended by a central angle of 0.5 radians. So we are looking for the length of the arc. So s is equal to r times theta. S would equal to 4 times, my theta is 0.5. So it would simply be 2 meters. That's all there is to it. Look at example 4. You walk 5 miles around a circular lake. So if I draw my circular lake here, and if I walk 5 miles, so let's say that I start right here, and I walk 5 miles. Hopefully you can agree that that 5 is actually the arc length because you're walking around the length, okay? Give an angle in radians which represents your final position relative to your starting point if the radius of the lake is 2 miles. So what they are looking for now is this theta. It tells us that the radius is 2. So I can again use my s equals r theta, except this time I know s is 5, is equal to 2 times theta. And if I divide by 2, my theta is going to be 2.5. Now again, it's 2.5 radians. It asks us for us in radian measure. So that's just manipulating that formula a little bit. Okay, so now let's talk about how to convert degrees to radians and vice versa. Hopefully you remember this. So In a circle, the outside measurement of one complete revolution can be represented by the circumference. I hope you would agree with that. So if I just go one complete revolution around, that's just simply the circumference of the circle. The circumference formula for the circle is 2 pi r. So this means that one revolution around the unit circle, now remember the unit circle means it has a radius of 1, would simply be 2 pi. So one complete revolution around the circle is 2 pi radians. And we already know that in degrees, one complete revolution is 360 degrees, which tells you then that 360 degrees is the same as 2 pi radians. So this means that one revolution around the unit circle is 2 pi radians, or 360 degrees. Simplifying this relationship by dividing both measures by 2 leaves us that 180 degrees would simply then be pi radians. It's just dividing both sides of this by 2. Taking it one step further then, if we use that equality found in part 3, we can find the conversion formulas for degrees versus radian. 1 degree is pi divided by 180 radians. And 1 radian is 180 divided by pi degrees. So they're inverse operations. So simply, here's what you're going to do. If I want to take, and if I want to change degrees, and we're not going to do all of these, degrees to radians, you simply take 180 and multiply it by pi over 180. So if you cancel the zeros, we know 2 divides into here 4, and 2 divides into 18, 9. You will get 4 pi ninths radians. Let's do the negative 30. If I take negative 30 over 1 and multiply it by pi over 180, 30 cancels into the 180 6 times, and it's negative pi 6. So I'm assuming you can do B and D if you really wanted to. Now let's go backwards. If you look for example 6, here we are given the radian measure and we want to change it to degrees. To do that, you simply multiply by 180 over pi. The pi's will cancel. 5 cancels into 180 36 times, and negative 3 times 36 is a negative 108 degrees. If we do 8 pi thirds, multiply it by 180 over pi, the pi's again cancel. 3 divides into 180, 60, and that would be 480 degrees. Now, don't let this one confuse you. Just because there isn't a pi in it doesn't mean that it's not radian measure. Notice there's no degree symbol. There would have to be a degree symbol if it was in radian measure. Okay, so you would simply multiply this by, again, 180 divided by pi, just like you did all of the other ones, and this is 114.6 degrees if you multiply that out.